And so the calculation for boron is going to look like this. If boron 10 is 18.9% of what's out there, we'll use that in decimal form, not percent form, just to make the math easy. 18.9% times its own mass. Boron 11 18.9% of all boron weighs this much. 81.1% of all the world's boron weighs that much. Any mixture, any sample of boron you take is a mixture of these isotopes, and there will be more boron 11 in there than boron 10, and that's why the average is skewed closer toward 11. Compare that number we calculated to what's on the periodic table. Ta-da! That's where it comes from. It's an average of the isotopes that are out there. And that's useful mathematically as long as you remember there really is no atom of boron that really truly weighs 10.811. It's an average mass to help you do the math reliably, knowing that you're dealing with a mixture. Question about where that average atomic mass comes from. Yes?
So you could have two masses that were bigger than just 10 and 11, and you would still find the same answer?
For boron, 10 and 11 is all that exists. Okay, you really don't have any options, all right? But like for other elements with chlorine and all, you've got chlorine 35 and you've got chlorine 37. That's the two isotopes that exist. And the percentages of those are such that the average falls out as what's on the periodic table.
Will we need to know any of that?
You will need to know how to do the calculation. You will not need to know what the percentages are, no, if that's what you mean.
Okay, yeah, like the 10, 11, how do I know?
I would tell you. Now, 10.811, if you had to round that off to an integer, the closest integer is 11, right? So you shouldn't be surprised that there is a boron 11 isotope, because this average is pretty close to 11. But yeah, I'm not going to have you predict what the mass numbers would be.
You're going to give the percentage too?
Unless the problem has you working backwards where you calculate percentage. But yes, I would give you enough information to plug into that equation at the top. That if I give you the percents in mass, you can calculate the average. Or if I give you the masses and the average, you can calculate the percents. Do number 12 on your own. What's on the board right now is the information that's explicitly given to you. There's 5 terms in this equation, and you were given numbers for 2 of them. And solving for the mass of chlorine 37, which looks like we don't quite have enough to work the problem. Emphasis on looks like, because you really do. What do we plug in here as the percent for chlorine 37? 2427. Thank you. And you know that because of how percentages work. Percentages have to add up to 100. And what do we plug in here for average atomic mass?
3.5.
Which comes off the periodic table, right? The periodic table tells you the average atomic mass. And then it's just math from there. Any question in getting your information filled in here? Because as far as this problem goes, right now on the board, we've done all the chemistry in the problem. All that's left is the algebra, the math on it. But you've done what you need to know as far as the chemistry. Especially, is there a question about where we got that 35.453 as the average atomic mass? Average atomic mass values are on the periodic table. Mass number is not, but average atomic mass is. And going through the math, you should end up with something close to 36.96. Give or take a little bit for possible rounding in the middle. Question about that? Now, number 13, I'm going to leave for you to work on your own. I do want to point out one thing to help you get started on this, though. Because in this one, it's asking you to solve for both percentages. So similar to this last problem, your 2 percentages are going to be related. So the way percentages work, if one of them, just for pretend, if one of them were 60%, then the other would have to be 40%, correct? Have to be. 60 and 100 minus 60 would be your 2 percentages. And so what you can plug in for these 2 terms, since we want to treat it in decimal form rather than percent form, is x and 1 minus x. And if you do that, then that's a single variable. You solve for x. That would be the percentage for one of them. And then you subtract to get the percentage for the other one. So x and 1 minus x is the key to working problem 13. Make note of that. Work that one on your own later. The next section is about moles. And this is where it tends to get a little sticky for people because we're starting to do calculations on units that you're probably not comfortable with. But to start with, just as a comparison, we're used to this conversion, correct? We're comfortable with that. Another way of writing that conversion, though, is this. Which is a rather peculiar way of looking at it, but basically, yeah, if a foot is 12 inches, then 1 inch is 1/12 of a foot, correct? Each inch is 1/12 of a foot. If you put 1/12 in decimal form, that's where the 0.833 comes from. Which is exactly the same relationship as the one above it, but looks funny. And we're just not accustomed to that. So what we're going to be doing with moles is looking at where the mole unit came from relative to something like grams that we are used to. And hopefully that'll give you a little bit of footing about where the number itself comes from, and then applying that to things and hoping for the best, I guess. Hoping that it makes sense, or hoping that you eventually get comfortable with it. All right. Now, we talked about the atomic mass unit scale last time. We talked about how it was based on atomic structure. It was a tremendously smaller unit than grams. You have this conversion given at the top of the mole page. That's just for illustration. That is not something that you want to remember. But 1.6605 times 10 to the minus 24th power is not much. 1 AMU is a very small portion of a gram, correct? But this is a conversion that you can use to relate the atomic scale, which is the way protons, neutrons, masses add up to be atoms. Relate that to the lab scale where you go in and you work and you weigh things in grams. So that's the conversion between the atomic level and, I guess you'd say, the lab level. The other way of expressing that, if we base it on 1 gram, as opposed to 1 AMU, flipping that conversion, just like I flipped this one over here, then how many AMUs would it take to make a gram? Comes up to be this. One inch is only a 1/12 of a foot. But together, 12 inches would make the entire foot, correct? 1 AMU is a very small part of a gram. It would take this many AMUs collectively to generate 1 gram unit. Now, if you've had chemistry before, then that number you've seen before. And that's going to become a crucial conversion for us. Not so much in AMUs to grams, but in the units that we call moles. 1 mole is defined as being that many things. One mole is defined as that many particles. It doesn't matter what they are. It doesn't specifically apply to AMUs, but it's derived from AMUs. The AMU to gram conversion is where it came from. That was not arbitrarily picked as somebody's favorite number. The math just worked out that way. And that's our reference point. This number, this relationship, you do need to memorize. Because we're going to be using that a lot. So you're given some information here, some comparisons, working on that definition for boron in the notes, where it says that one atom of boron, this is a general, generic, average atom. Let's say one average atom of boron was 10.811 atomic mass units. Because we've defined the mole the way we have, that means 1 mole of boron, which would be 6.022 times 10 to the 23rd atoms, would come out to be 10.811 grams. The periodic table gives you 10.811 as the average atomic mass for boron, and that number works both on the atomic scale and the gram scale as long as we define them all like this. It's convenient to help us with the numbers. One atom was 10.811 AMUs, but 6.022 times 10 to the 23rd atoms is going to weigh 10.811 grams. So the reason a mole is defined as that number of particles is so that the periodic table will tell you an average atomic mass that you can read in either AMUs or grams, depending upon what you're working with. And it makes the conversions more shorter, really. Because so that way you don't ever have to use that AMU to gram conversion. If you're working with one atom, you treat it as AMUs, but if you're working with a bunch of them, you treat it as grams. And the math will work out the same either way. All right. I know that's terribly vague at the moment, but hopefully once we start applying it, it will get some better. So, as a matter of, I guess as an analogy, the part where it says preliminary practice problem, try this. Just on your own. I'll put the numbers on the board. But this is just a beaker full of BBs. If you wanted to know how many there were, one way to find out is to count them, correct? And they wouldn't be so bad, except they roll all over the place, and then you may lose count and whatnot. But you could count them. But what's another way to do it?
Volume.
Volume is, that would be a little awkward, but I guess it's possible.
Finding the weight.
Weight?
And then dividing it by the weight of 1.
By the weight of 1. Good. You can do it mathematically based upon how much they all weigh compared to how much one weighs, right? And I'll give you the numbers, and I want you to calculate this out. But counting would be no problem, really, for this. But what if you had a 55-gallon drum full? You wouldn't want to count that, right? Even though you could, you wouldn't want to. Math is the better way to go. And you can do that based on rate mass for all compared to mass for one. So the numbers are this. Total mass of the BBs is 232.9 grams. That's not counting the beaker. So I weighed them all, but then I also weighed 12 of them. And the reason I didn't weigh just one, two reasons really. First of all, they're not all going to be identical. They look identical, they'll feel identical, but they won't be exactly identical, especially on the balance where you can get 2 or 3 decimal places. And so by weighing 12 of them, that gives me a better idea of average mass. But also, if I had only weighed 1, I'd be getting 3 significant figures in the mass, whereas by weighing 12, now I've got 4 significant figures in the mass. And so not only am I going to have a better number for the mass because it's an average, but I've also got more significant figures in that point as well, right? And that's kind of beside the point. But a dozen is always 12, and in this case, a dozen BBs weighed this much. Don't shortcut anything, but use those 2 conversions to calculate how many BBs there are. This is basically just dimensional analysis. You're starting with a unit of grams, which means you've got to arrange things to where grams cancel out. And if you look at your 2 conversions, only one of them even has grams in it, right? Only one of those 2 conversions involves grams at all. So there's not going to be there's not going to be any option in terms of how you stack these conversion factors. Got a number? Any question about how to set this up and do this calculation?
The grams go on the bottom like there.
Yeah, it has to. Otherwise, you've got nothing to cancel with this grams, right? And since grams has to go here, this conversion doesn't involve grams whatsoever. So since you have to have grams down there, it has to be this conversion and it has to be this part on the denominator. There's no options to how you stack that. If you've not got an answer to this, take another minute or 2 and keep working. Is it like 600 and something? What is it exactly?
I got 686.
686? 10, that's convenient. Good. Okay. You did too?
Yeah.
Okay. 686.0. Is there a question about how to get that? Because this is grams, we have to use grams as a denominator unit. So 4.074 goes here. 1 dozen BBs would go there. And then we would use the other conversion with the dozen part down. 1 dozen being 12 individuals. So it would work like that. Grams cancels grams, dozen cancels dozen, your answer comes out in individual BBs. Now, if there's a question, please ask, because this is important. All right, if you got that worked out correctly, then stepping into mole conversions is not going to be that big a deal, because it works exactly like what we just did. The concept is a little different because you're talking about atoms which you cannot see as opposed to BBs that you can. But those two conversions that we just used are pretty much parallel to average atomic mass and what's called Avogadro's number, which is this 6.022 times 10 to the 23rd. Average atomic mass, another name for that you'll see very often is called molar mass. It's the same thing. It's also called formula weight, it's also called molecular weight, it's also called atomic weight and atomic mass, and how many other names does it have? Formula weight, yeah. Did I say formula weight? Yeah, okay. Well, there's at least 6 different names for that conversion, all right? Don't let the terminology blur on you. But that relationship, those two conversions that you just did, are very parallel to Avogadro's number and molar mass. Because Avogadro number tells you how many particles are in a mole, and molar mass, or average atomic mass, tells you how much that mole weighs. And that's what we had with dozens here. One of them told you that a dozen was 12, and the other told you how much that dozen weighed, correct? Exactly parallel. The second part here, then. I guess I'll set it up here. If 4.074 was the mass of 12 BBs, then 1 BB is 0.3395 grams. Now those BBs look like copper, so we're going to pretend that they're perfectly pure copper. So instead of trying to figure out how many BBs are in the beaker, now we're going to try to figure out how many atoms of copper are in each BB. And that's something you can't possibly count, so you got to rely on the math. At least when we're counting the BBs, we had the option of pouring them out and counting them. You can't do that now. How many atoms of copper in one BB? We need our mole relationships, and this is them. 1 mole of copper is this many atoms how much is that mole of copper going to weigh? And you turn to the periodic table, that's right. 63.546 grams is 1 mole. The average atomic mass that's on the periodic table, also known as molar mass, that's the collective weight of 1 mole of that element in gram units. So 1 mole, by definition, is 6.022 times 10 to the 23rd atoms, and that 1 mole is going to weigh 63.546 grams. Avogadro's number is the same for everybody, but molar mass is not. It depends